Hi everyone, welcome to another session of the HBL files. In today's session, we will be deriving the kinematic equations of motion, namely the following. V is equal to u plus at, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is time. Next, we have s is equal to ut plus 1/2 at squared, where s is the displacement. Another equation for displacement, we have s is equal to the quantity v plus u over 2 times t. And lastly, we have v squared is equal to u squared plus 2as. Let's begin. Here we have the velocity versus time graph of an object with a non-zero initial velocity u. And then it has a final velocity v. Now, the object reached its final velocity at time t. Now, let's look at the gradient of this graph. To find the gradient of the graph, we simply pick two values from the y-axis or from the velocity axis, and then two values from the time axis. So for convenience sake, we can do the following, or we can choose the following. Final velocity minus initial velocity over the time for final velocity, which is t, and the time for initial velocity, which is 0. So simply t. But remember that in a velocity versus time graph, the gradient is equal to the acceleration, which means acceleration is equal to v minus u over t. And this is basically the definition of acceleration, the rate of change of velocity. Now, rearranging this equation, this will give us the first kinematic equation of motion, which is v is equal to u plus at. Okay. Next, let's look at the area under the graph. Notice that the area under the graph can be divided into two parts. The first part will be this triangular area over here, and then the next part will be this rectangular area. So if we assign the triangular area to be area 1, then it will be equal to 1/2. So for a triangle, it's 1/2 base times height. The base will be time t, and then height will be the difference between v and u. Next, for area 2, which is this rectangular area, it will simply be u times t. Now, notice that when we multiply or when we find the area under the graph, we are essentially multiplying the velocity times time. When we multiply velocity times time, the result is displacement, which means the area under the graph represents displacement. So if we get the total area under the graph, we are actually getting the total displacement of the object. The displacement is represented by S. So total displacement will be the combined areas, and that will be ut plus 1/2 times the quantity v minus u times t. Remember in our previous equation, we have encountered this. Acceleration is equal to the rate of change of velocity. Rearranging this equation, we'll now have at is equal to v minus u. We can then replace this v minus u by at, giving us the second kinematic equation of motion, which is s is equal to ut plus 1/2 at squared. Next. Now let's look at this value over here. What is this value? This is this broken line indicates the average value between the initial and final velocity. Okay, so this is like the value at the middle of initial and final velocities. Now, as you can see here, the gradient of the graph is constant, meaning acceleration is constant. That means for equal changes in velocity, it will happen for equal time intervals. What do I mean? Say, for example, you look at this initial velocity up to this average value of the velocity. The time interval, or the time it takes for the velocity to change from this initial value to this value, will be equal to the time it will take for this average value of velocity to increase to this final value of velocity. What does that mean? That means if you look at this graph over here, or this boundary over here, the time it takes for the velocity to change from u to this average value of velocity, that will be from this point going here. So that time interval will be equal to this time interval over here, from this point going to t, because that time interval is the time it takes for the velocity to change from an average value going to a final value v. Okay? Which means if you look at this white triangular area and this green triangular area on the top of this boundary, you can actually see that this length will be equal to this. And this one is equal to this part over here. Which means this small triangular area can actually fit here. We now have a one big rectangular area. Now, to find this area, we can simply multiply the value of this side, which is the average velocity, times the time. Okay? Now, notice again, when we find the area in this scenario, we are essentially multiplying velocity to time, which means that we are looking for, or we are actually getting, the displacement. So displacement can also be equal to the quantity v plus u over 2 times time. Again, we have considered the same area with the previous equation of motion. Okay? We did not change the area. We just adjusted the area so that we can have a one big rectangular area. Okay? Again, we adjusted it in the sense of changing the shape, not the area itself, or the size of the area. Okay, now this is our third kinematic equation of motion. Now, to get the last one, we'll make use of this equation and remind ourselves of the acceleration equation, rearranging this equation and isolating t. We have t is equal to v minus u over a. We then replace this t by this expression, giving us this one. Notice that the numerators v plus u multiplied to v minus u are actually factors of the difference between two squares. So multiplying these two gives us v squared minus u squared over 2a. Cross multiplying and rearranging the equation, we now have v squared is equal to u squared plus 2as, which is the fourth kinematic equation of motion. Again, here are the four equations of motion. And in case you didn't notice in the solutions that we have done, or in the graphs that we have seen, we only considered a constant gradient, meaning constant acceleration. So we were able to derive these four formulas using that condition. Consequently, these equations can only be used when the acceleration is constant. Okay, so that's it. I hope everything's clear. Thank you for learning with me today, guys, and see you on the next session of the HBL files.